Now let's do a few examples to enhance our understanding of rotational kinematics. Now we take the rotation of our Earth around the Sun. Now we can assume the Earth is doing almost a uniform circular motion with radius 1 astronomical unit, which is roughly 1.5 times 10 to the 11th meter. So we want to find out what's the angular velocity. Then what's the velocity of the Earth? We kind of discuss it for next lecture. The velocity of the Earth is like 30 kilometers per second. And we want to find out what's the angular acceleration, and then what's the gravitational force between the Sun and the Earth. Now first what we know is, everybody knows 1 year you have 365 days, and then 1 day has 24 hours, 1 hour has 3,600 seconds. So you multiply everything together, you have 1 year is actually, how many seconds we have in a year is roughly 32 milliseconds. Not a small number, but not so much either, so time flies away fast. Now, what do we know? What's the angular displacement of the Earth in a year? Now, we definitely know, right? In a year, the Earth going around the Sun for one circle, so it's 2 pi. So its angular velocity is 2 pi over 1 year. If you put in the number, you find the angular speed or angular velocity of the Earth is 1.99 10 to the negative 7 radians per second. So the velocity, of course, v is r times omega. It's roughly 30 kilometers per second, consistent with what we learned in last chapter. And the acceleration is r omega squared, roughly 6 times 10 to the negative 3 meters per second squared. Now, of course, if you have a centripetal acceleration, there got to be a force provide such centripetal acceleration. You can even put a C here. So centripetal force is m times centripetal acceleration. You put the mass of Earth in, you find this centripetal force is 3.6 times 10 to the 22 Newton. And who is providing this centripetal force? Of course, it's gravitational pull from the Sun on the Earth. So if you calculate it using gm Sun m Earth over r squared, you will get the same number. Infinitely the same number for the gravitational force between the Sun and the Earth. Now the beauty of rotational motion is that for object, if you know the angular displacement of one part of this object, all other parts have the same rotational quantity variable. So the angular displacement of any part for this person sitting there is the same. The angular velocity is the same, angular acceleration is the same, and that's the beauty of rotate. However, we use rotational variables. Now, this slide basically summarizes everything we need for rotational kinematics. So there is a one-to-one correspondence for the kinematic equations. Now, of course, keep in mind, this is constant acceleration for linear motion. Constant acceleration. And this one is for constant angular acceleration. Kinematic equations for constant angular acceleration. And then we can relate those linear motion and angular motion. So displacement equals r times angular displacement. Tangential velocity is r times omega. Tangential acceleration is r times alpha. And we always have AC equals r omega squared. Tangential velocity, which means your velocity in this direction over square over r square. Vt squared over r give you centripetal acceleration. Now let's do one example to relate rotational quantity to linear translational motion quantity. So this is Earth spinning if you look directly above North Pole, and you have a city on equator, and then we have New Orleans, which is roughly 30-degree latitude from equator. So you have basically one city somewhere here on the equator and the New Orleans. What will be the linear motion quantity for those two cities? So what do we know? What do we know is our Earth rotates around North Pole for one circle in 24 hours. So which means we can find out what's the angular velocity. The angular velocity is 2 pi over 24 hours, right? And after you find out the angular velocity, you can use angular velocity to find out what's the linear velocity. And this problem asks us what's the translational displacement of those two cities. For the city on equator, you just use radius of this city times angular displacement, give you the displacement, and the velocity is radius of Earth times angular velocity, and acceleration is radius times angular acceleration, which for the spinning of Earth, angular acceleration is 0. The Earth is spinning at a constant rate. However, we should have centripetal acceleration, which is radius times omega squared. Now, you do the same thing for New Orleans. Just for New Orleans, the rotational radius, rotational radius for New Orleans is radius of Earth times cosine 30 degree. So this is a little bit smaller. So area number is a little bit smaller compared to previous slide, but the equations are the same. Okay. This example, I have shown it on another video, a separator called Examples on Rotational Kinematics. Please go and watch it there. And this one as well, this is also available on the Examples of Rotational Kinematics video. I'm going to solve this one here. A pendulum M is set into a uniform circular motion, so it's doing uniform circular motion around this path. Want to find the tension of this stream, find the centripetal acceleration of the circular motion, find the angular velocity. So this is actually, you need to do dynamic analysis. You need to do free body diagram on the pendulum bob. So when it's rotating here, there are two forces acting on it, tension and gravity, right? So, and it's in the y direction. At least see in the y direction there is no motion, no acceleration at all. So you have the net force in the y direction should be 0. You have t, because this is theta, this is theta as well. T cosine theta equals mg, just in the y direction, give you t equals mg over cosine theta. And then we want to find out centripetal acceleration. And you see in the x direction, you don't have any other force. The net force in x direction is t times sine theta. That's the net force in the x direction. So when you have a force, you got to have acceleration, and then we know the acceleration is mac. the acceleration is AC, so the centripetal force is MAC. So you have T sin theta equals MAC. So you have T sin theta is mg sin theta over cosine theta. So this is T. This is T sin theta. So you have AC equals G tangent theta. After we find out AC, it's very easy for us to find angular velocity because we know AC is r omega square G tangent theta. So we have omega is square root G tangent theta over r. Okay. And that's what I want to talk about, rotational kinematics. Now, of course, good luck with this chapter and good luck with all your finals.